Hello, my name is Benjamin Krawciw, and this is my presentation that I gave at the 2021 March meeting on interferometer networks. I did this research at the Colorado School of Mines under Professors Cecilia Denise Behn, Gong, and Lincoln Carr. This was a joint effort between the Departments of Applied Mathematics and Statistics and the Department of Physics. I'll start with some background on my research. It's in the area of complex network theory, which has been used to describe social networks, technology networks, trade networks, and spontaneous synchronization. But my group wants to use it to detect phase transitions in quantum many-body systems. The problem is that nobody has properly accounted for networks with phase in complex network theory. So my work began by generalizing some of the complex network measures and a notion of networks for complex number edge weights that can represent amplitude and phase of signals propagating throughout them. Once I generalized this mathematics, I needed a physical problem to look at it with. I wanted something classical, something intuitive to some extent, and so I chose interferometers. Before going into the complex network theory, I should talk about what a network is. The concept will be familiar to many of you as graphs. These will have nodes, these abstract objects connected by links, or I might call them edges or connections. These are all synonyms in the literature. These dots represent the nodes, the lines between them represent links. These links will sometimes be weighted, and that weight will usually represent the strength of the connection, although it can represent some other property related to that. These networks are sometimes directed, meaning that a connection from 2 to 1 will not be the same as a connection from 1 to 2. And to represent them, one can either use a graph, the dots and lines drawing, or an adjacency matrix, where the row and column will represent the node in and out of an edge, and the value inside will represent the weight, or in the case of unweighted networks, just a binary 0 or 1 for the existence or non-existence of a connection. Now I should talk about what makes a network complex. It's easiest to start with what it is not. A complex network is not just a big network. An example of why this is a lattice. They can be quite large, but all of the complexity is reducible down to a single node and its neighborhood. It is also not a random network. Randomness in its own way is predictable. However, it is what is often seen in the real world, and this is visible in non-trivial topology. What this means is there are some features that are sort of difficult to understand without some sort of extra modeling. Examples of this are the small world property, the idea familiar to the general public as the 6 degrees of separation concept, where things are highly clustered and there seem to be low path lengths between all of the nodes in the networks. And in real world networks, we also see distributions of degree that are sort of interesting. There will be these large hubs in the middle of a network, whereas a small number of nodes will have most of the connections and the rest will sort of be peripheral. So to talk about these networks, we define network measures, and I'm going to talk about 3 in this presentation. The first is degree. It represents how much a node participates in the network, and in its simplest form, it's just the count of the number of edges on a node. This can be either in or out for directed networks. The clustering coefficient measures the friend of a friend is my friend property. It's based on the occurrence and strength of triangular cycles. In its simplest form, the best way to think about it is, let's say you have a node here connected to 2 others. The clustering coefficient will measure the probability that these 2 nodes are themselves connected by a transitive edge. Lastly, there's path length. Path length is based on the notion of travel over a network. And in its simplest form, you just take 2 nodes and count the number of edges between them in a path. Now I'll talk about some of the tools that I've developed. So first, I defined the interferometer network. What is an interferometer network? Well, it has to be a network that represents signals propagating over it, has to depict systems with phase. So to do this, I'm using complex number edge weights with magnitude and a phase. As a signal travels over an edge, you simply multiply the signal by an edge weight. For example, on the network on the right, we have this red node, which acts as a source. Let's say it has a signal value of 1. Going from the red node to the blue nodes, the signal is split in half. Then going from the blue nodes to the green nodes, they're multiplied by these complex exponential terms and then added together again with the green node. To actually solve for the signal values, we use a matrix equation. So we'll start with the weighted adjacency matrix W. the vector of source connections, connections to the constant sources that don't change, S, and then we have a signal vector E that we're solving for. We just have the simple matrix equation WE plus S equals E. Now let's talk about how I generalize those complex network measures to talk about interferometer networks. For the degree, it's pretty straightforward. Instead of summing up whether or not an edge exists on a node, I'm summing up the complex number edge weights. As a result, this measure will represent not just how much a node participates, but how coherently it does. So a node may have many connections, but if the phases are all basically random, they'll sort of cancel out. The clustering coefficient was the least straightforward for generalization, because there are many generalizations to weighted networks, and I had to pick one before I generalized that further to complex number weighted networks. The one I chose was ultimately a weighted average of the weight of that transitive edge. It's weighted by the weights of these two edges. So in general, if you have a very strong triangle, that's going to contribute more to the average than a triangle with weak edge weights all over. When I generalize this to complex numbers, I kept that normalization term in the denominator real, but I kept all of the phases in the numerator. And so in effect, my clustering coefficient measures not only the size of the transitive edge, but also the total phase accumulated over the triangular cycle. For the path length, normally you would do it with addition, you'd add the edge weights. Or for the interferometer, where I'm multiplying by the edge weight every time I traverse, it makes most sense to multiply. So when I talk about path length, what I mean is I'm multiplying by the edge weights along the path. Now let's talk about some of the problems I've used these tools on. First, I made sure that I could recreate other results in interferometry. I made sure that my notation was equivalent for the Michelson and Sagnac interferometers, and it was. Then I looked at random interferometers. As I said before, random networks are not complex, but they're sort of a gateway to complexity, so it's good to start there. For this model, I began with a source node with a fixed signal value of 1. I introduced n-1 more nodes for a total of n, and I randomly connected them, so between any two nodes, there was a probability p that they were connected. When I weighted all of those connections, I used a normalization term, 1 over np, and then I multiplied by e to the I phi, where theta, where theta is just a random phase. On the right, we see some plots. The first two rows are the in and out degrees for the unweighted, weighted, and complex number generalizations. We see that there's just an NP proportionality in the unweighted versions, as is true for just the traditional unweighted random network. Then for the real version, because of that normalization term, they stabilize to 1. And then my complex number measures converge to 0 because of that effect I mentioned before, where they have random phases and so they cancel out. For the clustering coefficient, we see similar stuff, where there's just a straight proportionality for the unweighted version. The real version just converges to a constant value, and then the complex version converges to 0. For the actual signal values, when you calculate them and plot them, for an example I did, there was a uniform distribution. And so what we see is that these random interferometers, you can't really extract any useful information out of them. Everything's randomly distributed, just as one would intuitively expect. The next problem I looked at was given to me as a challenge. For an interferometer where you're making a measurement by changing some phase, that total phase change is some phi. And when you're taking the measurement, the output that you're getting is theta. I was challenged to create an interferometer where theta was greater than phi. And what I came up with was this n-stage skew cycle interferometer. It has the relevant parameters phi, the total input phase, output phase theta, the number of stages n, and the skew parameter d. When you have a very large n value, your theta will converge to 1 plus d times phi. Now this network is more of a mathematical curiosity. It'd be very difficult to build, and because of error propagation, you'd find that differences between the stages of the skew cycle interferometer would be amplified on the output. And so it'd be very hard to actually get measurements out of this thing. But it does serve as a counterexample to the idea that your input phase phi is an upper bound on the output phase theta. You could have something larger, so you might have unpredictable effects in large interferometers. Now I'd like to talk about what I'm currently working on. I am working with a model called the Watt-Strogatz network, which in the literature is used to model small world networks. So this model has a high clustering coefficient and low diameter, where diameter is the largest, shortest path length in the network. So the longest distance between two nodes. And what I've done is I've started adapting this to an interferometer, and I'm going to measure the path length, clustering, and degree. And then I'm also going to calculate the signal values and see if I can draw some connection between them to make some statements about what clustering, path length, and degree mean for an interferometer. All right, to conclude, I have developed this notation of interferometer networks to examine large and complicated interferometers. The notation works for old results, meaning that it's still equivalent to our current understanding. And I've demonstrated that random interferometers contain little useful information, confirming the intuitive reasoning about them. I've also exposed the promising possibility that these complex network measures could provide a way of characterizing interferometers. Thank you very much.